Welcome to Study Loop.
Hi everyone. What we have right now is a collar of mass 5 kilograms that is not attached to a spring K1, which has a spring constant of 400 newtons per meter. And there is a constant force of 150 newtons that is applied via a cable. What we're asked to find is the spring constant of the second spring, knowing that the velocity is 1 meter per second when the spring K1 is compressed 75 millimeters. So what this looks like in a diagram is we have our top spring of K2, which is what we're trying to solve for. We have a bar, and then we have a collar on this bar. And this collar is attached to, or is resting on top of spring K1, which we know. And these are our distances. We know that this is 450 millimeters, and the spring K1 is compressed 75 millimeters. And at that point, we know that the velocity of A, which I'm just going to call right here, is 1 meter per second when it's being pulled on top of a cable that has a force of 150 newtons. And there is a pulley here, but we're going to assume that the mass of the pulley and the friction are negligible, so we're going to ignore those. So what we're going to do is use the method of work and energy and apply it to collar A. So we're simply going to say that kinetic energy at 1 plus the potential energy from 1 to 2 is going to equal the kinetic energy at 2. We know that the collar is starting at rest, so T1 is just going to be equal to 0. So now we're just going to analyze position 2. We know that in position 2, the upper spring is going to be compressed 75 millimeters. Because remember, that is a given statement that we have. And at that point, we know that the velocity is also 1 meter per second. So we know that T2 is just going to be equal to 1/2 mv2 squared. Remember that we know the mass is 5 kilograms, we know the velocity, so we can just get this as 2.5 joules. So now we're going to look at it when the collar is raised from basically 1 to 2, so from position A to position B. The force of the weight is going to be equal to negative mgh, where mass is 5 kilograms, g is 9.81 meters per second squared, and the height is 450 millimeters, because that's also given to us in the problem. And what this is going to result in is a change in potential energy equal to negative 22.0725 joules. So we know that in position 1, the force exerted by the lower spring is equal to the weight of the collar, and we can just draw a free body diagram to show that. So in position 1, we have the weight of acting down on the collar, and then we have the spring force of K1 pushing up, and I'm just going to call that Fs. So we can rewrite this as saying that F1 or Fs is going to be equal to the weight, and that is equal to negative mass times gravity, and that's going to be equal to negative 49.05 newtons. Now we know that when the collar moves up the distance x, the spring force is going to change, and that's simply going to be equal to Fs minus Kx. And that Fs is what we solve for here, that negative 49.05 newtons. And it's going to be that until the collar separates at xf, which is going to be F1 over K1. So if we solve for that, we can say that xf is going to be equal to F1 over K1, which will be equal to, we know F1 is 49.05 newtons, we know K1 is 400 newtons per meter, and this will translate into 122.625 millimeter. Now, we can solve for the work exerted by the spring force by using this expression. So we can see that U from 1 to 2 of spring 1 is equal to 0 xf of F1 minus K1x dx, and this integral So for plugging in the quantities that we know, actually we can just go ahead and solve this integral in terms of its variables. So we can say that this is equal to f1 minus k1 x squared over 2, evaluated from 0 to xf. Now if we plug in these limits, we can see that this is going to be equal to, this is going to be f1x. This will be equal to f1xf minus f1 k1 xf squared over 2. Oh, excuse me. Take this f1 out of here. This is going to be f1 xf minus k1 xf squared over 2. And we know, and that's simply what it's going to be. And we can plug in for the quantities that we have. We know f1, we know xf, and we know k1. What we get is a total work of 3.0074 joules. Now in position 2, the upper spring is compressed by 75 millimeters. And we can simply use the, again, this work formula to solve for the work of the force exerted by the spring. And I can say this as u from 1 to 2 is equal to negative 1/2 k2 y squared, because we're just compressing the spring and there's no weight force acting on it. And we know that the spring compresses by 75 millimeters, so we plug that in for y. And what we get is negative 0.00028,125 K2. Remember, K2 is what we're trying to solve for. And this is equal to U1 to 2 of spring 2. So next what we're going to do, we also have to account for the work of the 150 Newton force that's applied via the cable. So at position 1, we need to solve for length AB, and we can just use that with the given quantities that we have in Pythagorean theorem. So I'm just going to call that length AB at 1 is equal to the square root of 450 squared plus 400 squared. And this gives us a length AB of 602.08 millimeters. At position 2 now, length AB is going to be equal to 400 millimeters because it's directly horizontal. So what we're going to do is solve for the displacement. So the displacement is going to be the length at AB1 minus the length at AB2. And this gives us a displacement of 202.08 millimeters. I'm just going to write this in meters because that's where we're doing our calculations in. So that's going to be 0.20208 meters. Now, again, we just solve for the work done by this force. So that's just going to be U1 to 2 of this P force will be equal to P times D. We know P is 150 newtons. We know that D is this 202.08 millimeters. Plugging that in, we get a total work equal to 30.312 joules. Now, if we look at the total work done in the entire system over the course of this motion, we can see that U12 is going to be equal to the work done by the gravity, which is going to be negative 22.0725 joules. The work done by the lower spring, so that's going to be plus 3.0074 joules, minus the work done by the upper spring, which again is unknown. That's going to be minus 0.0028125 K2, plus the work done by the cable, so plus 30.312 joules. Now, we know that using the principal work and energy, as we did in the beginning, that U1 to 2 is equal to T2. Now remember that we know what T2 is, that's just 1/2 mv squared. We know that the mass is 5 kilograms, the velocity is 1 meter per second, so that quantity T2 is numerically defined. U12 is right here, and the only unknown that we have is this K2. So by setting those expressions equal to each other, we can solve for K2, and we get that K2 is equal to 3110 newtons per meter. And that is our final answer.